Welcome to G Fun Facts Online. Did you know there are giant, invisible holes in the middle of the ocean? Not holes in the water itself, but holes in gravity. Vast regions where the pull of our own planet is mysteriously weaker than it should be. From space, Earth looks like a smooth blue marble. But this is an illusion. Our planet's gravitational field is actually a complex, lumpy, and dynamic tapestry. And nowhere are these lumps and bumps more fascinating than beneath the waves. An unseen force, a silent variation in one of the universe's fundamental constants, is continuously shaping the face of our oceans, creating vast hills and valleys on the sea surface that betray the hidden architecture of the world below. These are marine gravity anomalies, and they are cryptic messages from the deep Earth, telling tales of sunken continents, hidden mountain ranges, and the slow, majestic churn of molten rock deep within the mantle. Today, we're diving into a world where the primary tool isn't sonar, but the measurement of the very force that holds the cosmos together. We'll explore how we measure these invisible forces, and what they tell us about the inner workings of our planet. Let's start with the basics. We all learn that gravity is the force of attraction between two objects, depending on their mass and the distance between them. In a perfect world, a flawless sphere of uniform density, gravity would be the same everywhere on the surface. But our Earth is not perfect. Several factors disrupt this uniformity. First, its shape. Earth's rotation causes it to bulge at the equator and flatten at the poles, making it an oblate spheroid. Since the equator is farther from the planet's center of mass, gravity is slightly weaker there. Second, the rotation itself generates a centrifugal force that pushes outwards, counteracting gravity. This effect is strongest at the equator, further reducing the pull. But the most crucial factor for scientists is subsurface density. The Earth's crust, mantle, and core are not uniform. Continental crust is thick, but less dense than the thinner, denser oceanic crust. Deeper within the mantle, variations in temperature create regions of hotter, less dense rock, and cooler, denser rock. A gravity anomaly is the difference between the actual, measured gravity at a location and the theoretical value we'd expect on a uniform Earth. These anomalies are incredibly small, measured in units called milligals. To give you some perspective, Earth's average gravity is about 980 gals. The anomalies we're talking about are just tiny fractions of that, but they are immensely significant. A positive anomaly means gravity is stronger than predicted, suggesting an excess of mass, like dense rock, is hiding below. A negative anomaly means a weaker pull, implying a mass deficit, like less dense rock or even a deep trench. By mapping these subtle deviations, we can build a picture of the unseen world hidden deep beneath the sea. So how do you measure such a tiny fluctuation while on a heaving ship, thousands of meters above the feature you're studying? The story of how we first charted the ocean's gravity field is a testament to scientific ingenuity. It begins with a Dutch geophysicist named Felix Andries Venningmanis in the early 20th century. At the time, measuring gravity on land was common, but the sea remained a blank slate. The rolling and pitching of a ship would completely overwhelm the delicate instruments, called gravimeters. Venningmanis devised a brilliant solution. He created an instrument with two pendulums swinging in sync, but with opposite phases. By measuring the difference in their motion, the horizontal accelerations of the ship canceled each other out, isolating the underlying gravitational force. But he still needed a stable platform. The answer came from an unexpected place: the Royal Netherlands Navy. Venningmanis realized that a submerged submarine would be shielded from the wind and waves, providing a remarkably stable environment. Starting in 1923, he embarked on a series of extraordinary expeditions. In cramped, uncomfortable submarines, he and his crew sailed the world, making hundreds of painstaking measurements. He discovered long belts of strong negative gravity anomalies running parallel to deep-sea trenches, particularly in Indonesia. This was the first compelling evidence that the Earth's crust was being actively forced downwards in these regions, a foundational concept for what would later become the theory of plate tectonics. He was also the first to identify a huge area of low gravity in the Indian Ocean, a mystery we will return to. Venning Meinesh single-handedly opened the oceans to geophysical exploration. While his methods were revolutionary, they were incredibly slow. Today, we have two primary methods. The first is modern ship-based gravimetry. The instruments are now incredibly sensitive, but the main challenge remains the ship's motion. Even on a calm day, swells can cause accelerations thousands of times stronger than the gravity anomaly being measured. So the gravimeter is mounted on a gyro-stabilized platform that keeps it perfectly level. Scientists also have to account for something called the Eötvös effect. This is a correction for the ship's own east-west motion. If you're sailing eastward, you're moving with the Earth's rotation, which increases your centrifugal force and slightly reduces the measured gravity. If you're sailing west, against the rotation, the measured gravity increases. Accurately calculating this requires precise GPS data on the ship's speed and heading. But the most revolutionary tool for mapping global marine gravity is the satellite altimeter. This technology doesn't measure gravity directly. It uses a clever proxy, the height of the sea surface. Here's how it works. A satellite, like those from NASA or the European Space Agency, orbits the Earth, bouncing radar pulses off the ocean and measuring the return time. This allows us to measure the sea surface height with astonishing accuracy, down to a few centimeters. Now, if the ocean were completely still, with no winds, tides, or currents, its surface would conform to what's called the geoid. The geoid is the level to which water would settle under the influence of gravity alone. And this surface is not smooth. It has hills and valleys that directly mimic the gravity field beneath it. An underwater mountain, a seamount, is a huge concentration of mass. Its gravitational pull attracts the surrounding water, causing the sea surface above it to bulge outwards in a hill that can be meters high. Conversely, a region with a mass deficit like a deep trench has a weaker gravitational pull, causing the sea surface to be depressed, forming a valley. By measuring these subtle bumps and dips in the sea surface across the globe, satellites create an incredibly detailed map of the marine gravity field. This method has been transformative, allowing us to see the tectonic fabric of the entire ocean floor from space, revealing thousands of previously uncharted volcanoes. So, what do these maps show us? Let's take a tour of the undersea landscape, guided by gravity. First, the positive anomalies, places where gravity is stronger, indicating an excess of mass. Mid-ocean ridges, like the massive mountain range running down the center of the Atlantic, are a perfect example. This is where tectonic plates are pulling apart and new crust is born from upwelling magma. The gravity signature here is fascinating. While the entire ocean basin shows a strong positive signal because oceanic crust is so dense, there's a distinct relative dip in gravity right along the ridge's axis. This dip points to a low-density body beneath the ridge, a chamber of hot, partially molten magma that is feeding the creation of new crust. Scattered across the oceans are also tens of thousands of seamounts or underwater volcanoes. Being made of dense volcanic rock, they produce a distinct localized positive gravity anomaly. This effect is so reliable that satellite altimetry has become the primary tool for their discovery. The gravitational pull of a large seamount causes that visible bulge on the sea surface which satellites can detect. In recent years, this method has led to the discovery of nearly 20,000 previously uncatalogued seamounts. This isn't just map-making. Seamounts are biological hotspots, creating unique habitats that support vibrant, deep-sea ecosystems. Now for the negative side, regions where gravity is mysteriously weaker. Deep-sea trenches are the deepest parts of the ocean, formed where one tectonic plate dives beneath another. The Mariana Trench, the deepest point on Earth, has a classic gravity signature. Directly over the trench, there's an intense negative anomaly. This is because the trench is filled with low-density water instead of rock. Just next to the trench, there's a belt of positive anomalies. This is caused by the oceanic plate bending upwards, like a flexible ruler being pushed over an edge before it plunges down. And further on, a strong positive anomaly is found over the associated chain of volcanoes, caused by the cold, dense slab of crust diving deep into the mantle. This negative-positive-positive pattern is the clear fingerprint of a subduction zone, a place where Earth's crust is recycled. But perhaps the most enigmatic gravity anomaly on the planet is the Indian Ocean geoid low. First detected by Venning Minus in 1948, this is the largest and most profound gravity hole on Earth. It's a vast region, over 3 million square kilometers, where the sea level is depressed by as much as 106 meters, or 348 feet. For decades, its origin was a complete mystery. Recently, however, sophisticated computer modeling has produced a compelling explanation. The story begins over 100 million years ago, when the landmass that would become India broke away from the supercontinent of Gondwana. Between India and Asia lay an ancient ocean called the Tethys. As India raced north, the dense oceanic crust of the Tethys Ocean was forced to sink into the Earth's mantle. According to a 2023 study, these cold, dense slabs of the sunken Tethys seafloor plunged deep into the mantle beneath Africa. As they sank, they displaced vast quantities of hotter, less dense rock from a deep mantle structure known as the African superplume. This displacement generated plumes of hot, buoyant material that rose upwards, spreading out in the upper mantle beneath the Indian Ocean. It is this huge volume of hot, less dense mantle material that creates the mass deficit responsible for the giant gravity hole. The dip in the Indian Ocean is a surface expression of this colossal deep mantle structure, a ghostly echo of a long-vanished ocean. This study of subtle forces might seem academic, but it has profound implications. First, an accurate model of the geoid, that theoretical sea level, is the fundamental reference for all oceanography. Ocean currents are essentially water flowing downhill on the sea surface. By precisely mapping the geoid with gravity models, scientists can isolate the true dynamic topography of the ocean and calculate the speed and direction of major currents like the Gulf Stream, which are critical for regulating our planet's climate. This technology also helps us monitor climate change. Satellite missions like GRACE can detect tiny, time-variable changes in gravity. They can essentially weigh the ice sheets in Greenland and Antarctica, tracking how their mass is lost to the ocean and contributing to sea level rise. Finally, these gravity maps give us a window into the deep Earth. The largest anomalies, like the Indian Ocean low, are the surface expressions of deep mantle convection, the engine that drives plate tectonics. By combining gravity data with seismic imaging, geophysicists can test models of this deep flow. Peering into the very engine that drives continents, creates oceans, and builds mountains. The surface of the ocean, which appears so uniform, is in fact a dynamic and uneven map that speaks a hidden language. It's a language written in the subtle grammar of gravity, where dips and bulges in the water reveal the epic geological sagas occurring in the darkness below. From the fiery birth of crust at mid-ocean ridges to its dramatic demise in deep-sea trenches, these anomalies are the clues. The quest to measure this force, which began with daring submarine voyages, has now reached the precision of space-based radar. And in doing so, it has fundamentally reshaped our understanding of Earth as a living, breathing system. By continuing to listen to these gravitational whispers, we can decipher the complex processes that govern our world. The mysterious force beneath the ocean is, in the end, the pulse of the planet itself.